Okay, I lost my power. Power. So we were discussing about this particular decay process. So we cannot expect this process, this particular decay process, when K0 decaying into two pions, because they are short-lived. If you are having that cylindrical tube which is very large, so they are short-lived. So we cannot observe those pions, but we can still observe these three pions. So when they did this experiment, it is also found that sometimes this K0, sometimes this K0, which means that the KL, I'm talking about that long lead case, that is going to become two pions. They are sometimes decaying into two pions instead of three pions. This is observed experimentally. So in this particular case, we know what is this eigenvalue for this K0L. This is having -1. Okay, eigenvalue for Cp action, Cp symmetry. We have that eigenvalue which is correspond to this particular case Kl, which is -1, because it is like K2. We already observed that, because it is always gives three pions, and it is associated with 1, 3, 1 to the power 3. So that will give you -1 eigenvalue. So this K0L for long-lived case, that is -1. And in this case, we have two pions, so this will be -1 square. So this is not balanced. This is not conserved. Eigenvalue in this side is -1. In this side this is +1. So this is not conserved. So the eigenvalues are different. So Cp symmetry violates. Okay? So Cp action, which is not conserved in this particular reaction. Okay? So it is observed that sometimes those long-lived counts, K0s, they decay into two pions. That is also observed. But in such cases, Cp symmetry violates. Okay? Because they will not give you the same eigenvalues. So then we introduced that time reversal symmetry. In that time reversal, we already discussed this. In time reversal symmetry, how to change the time. Okay, let's say A decay into B plus C. Then after time reversal, your B plus C should be. Okay. So that we already discussed yesterday. Then because of the Cp symmetry, which is violating in some reactions, some interactions, so we cannot rely on that Cp symmetry again. First, we considered the charge conjugation, but charge conjugation was not there for the case some particular reactions. Similarly, for parity also, weak interaction both will be broken, because when you consider that weak interaction, we already discussed charge conjugation will not be there. Charge conjugation will not be possible, or it is not allowed in the case of weak interaction, because those electrons, like electrons, neutrons, those particles, they will not allow that CP symmetry, sorry, the C symmetry, charge conjugation symmetry in weak interaction. So in weak interaction itself, this uh, charge conjugation is violated. If we, when we look for that parity symmetry, parity symmetry also violates in weak interaction. We already discussed about beta decay processes, and we observed that the parity is violated in that particular reaction. Parity symmetry is not there. Then we considered C and P together, C3, C plus P. So Cp symmetry, whether Cp symmetry is allowed or it is conserved in these interactions. Then for almost all the interactions, it is okay, but then later it is found that for kaons, it is again violating. So that Cp symmetry also broken. Then we introduced the Cpt symmetry, okay, where C is the charge conjugation, P is the parity operation, then T is the time reversal. When we introduce these three together, as long as uh, any interaction you consider, so this, if you apply charge conjugation, then parity, then time reversal, but this order is not necessary. If you apply all these actions on that interactions, and up to now, there is no interactions which is going to be violated under this particular symmetry. Okay, so CPT symmetry is there for all those interactions. In that case, we have to apply all those charge quantification, parity, and time reversal operations. Okay, and for example, if you consider a reaction A, which is interacting with the B particle B, like this. So we use Feynman diagram here. This is the Feynman diagram for this particle interactions. This. And then this will produce two new particles C and D. This is a Feynman diagram for the particle interaction. So this is what is happening. Okay, this is the original interaction or original reaction. Then we have, for example, if you consider time reversal symmetry here, after time reversal symmetry, so that will give me just opposite of this, that C and D interacting. Okay, initially C and D particles are interacting here, and which will produce A and B. So when you do that time reversal, then when you apply that charge conjugation in this reaction, I'm saying in this original interaction, then we can have a charge conjugation will give you A bar here, then B bar here. All other things are same. Direction will be same because we have any problem with that. So this will be this. We have C and D, but will be antiparticle. So charge conjugation only change that particle into antiparticles. Okay. Here we have the direction which is changed because here time reversal. And then next we consider parity. If you apply parity operation in this particular interactions, then we'll have the parity. You consider that mirror here. Then you have to pick this A to B. You have to interchange these two and C to D. Then you consider mirror here. Then you have to interchange C to here, D to. That will be happening. So that will give you total under that parity operation. After parity, that that will come as so this will be having. Okay, I will just put this in C. This is in D. So here we have A. Sorry, this one also will be lifted. So this is B. So A will be going to interact with B, and that will produce C and D. Okay, only that this A which will come down and this B will go up. This C will come down and D will go up. Then again you flip to these axes so that this D will come here. Okay, so have D here. This one will be D. This one will be C. So first A and B interchanged, C and D interchanged, so D will come here. So then D goes this direction, C goes to here, and D, A comes here and D comes here. Okay, that's it. So that's what happens in parity operation, flipping of that axis. And if you have all these actions together in this particular original interaction, then we can have all these together, which means that this particular state you take, then you can have the bar here. Then we have C bar because you had to take conjugation of this. So then we have the bar, A bar. So here we have done both the parity operation as well as the charge function. Oh, okay. In parity operation, I will give that direction. Here. So this is what is happening. So in this case, you have to see this like this. Don't confuse with this direction. I will explain this. Okay. So initial state we have A and B interacting, okay, and giving you C and D. And when you have that parity operation, it will be like this. There is no doubt about this. So this will be your state after parity operation. And if you make the charge conjugation on this, then you will be having D bar, C bar, D bar, A bar here. Then you apply that time reversal. Then you will be having these directions. D will be D and C will be interacting and giving you A and B. So that is what is happening here. C and B bar and B bar is interacting, and it will give you B bar and C A bar. So that's very simple. So first you consider parity operation like this. Then you apply charge conjugation. So just that will come as D bar here, C bar here, B bar here. Direction will be the same. Okay. But when you apply that time reversal, then this time B and A is not interacting because when you apply that time reversal, C and D will be interacting and give you N. So this D and C will be interacting. Now it is D bar and C bar. That will be interacting and give you B bar and A bar. That is what is happening. So that will be your CPT action. Charge conjugation plus parity plus time reversal. That will be given like this. So up to now, there is no interaction which violates CPT theory. If any interaction which is going to violate CPT theory, then we have to rewrite those relativity equations, special theory of relativity, and the relativistic quantum mechanics. So that there will be many corrections if the CPT theory is violated in any of the interaction. But up to now, there is no interaction which violates CPT theory. So together with this charge conjugation parity and time reversal operations, we can have symmetry in any interactions. So any interactions, if you apply this CPT charge conjugation parity, that is flipping of that axis, and then time reversal. If you apply these three, then consider that particular interaction with those antiparticles or particles, then that will be also possible. Which means that the CPT theory, if you apply in any interactions, and whatever you are getting, in this particular you can see, we have original interaction like this, that A and B becomes C and D, Okay, so this reaction is valid. This reaction is possible. Now you apply CPT on this particular interaction, and we get like this. And if you have after CPT theory, if you get like this, then this interaction is also possible, which means that this D bar and C bar interacts each other and forms B bar and A bar. That interaction also possible, which means that this CPT theory or CPT symmetry is there for all the interactions whatever we observe. Okay, no interactions violates CPT theory. Okay, so that's all about this charge conjugation, parity, and time reversal, and CP violation, CPT. Now we'll discuss something more about the strangeness conservation and isospin conservation. We didn't discuss about their conservation. We just discussed about their calculations. Okay. So here we will discuss about the strangeness and isospin conservation. And remember that all these particle conservations are approximate conservations. They are not like energy or momentum conservation. So we will consider first the strangeness conservation. Okay. Before that, I will just give you a hand of the strangeness calculation. We already discussed about that Gell-Mann-Nishijima formula. So that will give you like Q equal to I3 plus E plus S by 2. From this, you can calculate strangeness. Okay. But I have to say that I is equal to, okay, I will say M equal to 2I plus 1, where M is the multiplicity. From this, you can find out what is I, minus 1 divided by 2. Okay, M is the multiplicity. Okay. And that third component or Z component of isospin is that is I3 or IZ. That will be, that can be calculated from this I. So it will be from minus I to plus I. Okay, so I3 will be equal to minus I2 plus I in steps of 1. Okay, like the normal quantum numbers that we have. For example, if you are having L value, then ML value will be from minus of L to plus L, like that. So here we have I, for example, K plus, if you calculate, K plus, you can see in this group we have K plus and K0 as the particles, and their antiparticles also there. But in the case of when we consider isospin, we will not consider the antiparticle, I mean, for calculations of isospin. So there are two particles in this group. So multiplicity is 2. So I will be equal to 2 minus 1 by 2. So this will give you 1 by 2. And I3, if you calculate I3, that will be varying from minus I to plus I. So it will be minus 1 by 2 to plus 1 by 2. So in steps of 1. So it is I3 will be having minus 1 by 2 and 1 by 2. These are the two possible values. So minus 1 by 2 and 1 by 2 are possible. And 1 by 2 will be associated with the K plus, and minus 1 by 2 is associated with K0 because highest charge will take the highest I3 component. Okay. But you can also calculate I3 by using one simple formula. Discuss that. So I3 can also be given by Q minus Q bar, where Q is the charge of group and Q bar is the charge of the particle. Sorry, just understand these two. Here Q is the charge of the particle and Q bar is the charge of the group. So this is Q. So that average charge. This average charge. Okay, so this is Q is the charge of that particle, whatever whichever particle we are considering. Then Q bar is the average charge of the group. Oh, sorry, this is so Q bar is the average charge of the group, and Q is the charge of particle. So in this case, for example, if you consider K plus, Q bar is the average charge. So K plus, the charge is +1, and we have next charge is K0, the charge is 0. So +1 plus 0 by total number of charges 2. So average charge is +1 plus 0 by 2. This will give you 1 by 2. Okay, this is for K1s. And for K plus, if you consider Q equal to +1, so Q minus Q bar, which will be equal to Q is +1 minus Q bar is 1 by 2. So this will be 1 by 2. So this is the I3 value. So for K plus, it is 1 by 2. And if you consider K0, then Q minus Q bar will be equal to Q is 0 now, minus 1 by 2. Okay, that will give you minus 1 by 2. This is the I3 value for K0. So this is how you can calculate I3 otherwise. Okay, otherwise you can use this equation also. Anyway, you can calculate. So this is much more easier way if you know the average charge and charge of the particle. Okay, so now we will discuss about the conservation of strangeness and isospin, the component of isospin, all those things. So let's consider the strangeness first. Strangeness conservation. So strangeness conservation means that your delta S should be equal to 0 if it is conserved. Okay. So that means if you have any interactions, any reactions, then if your delta S is equal to 0, then it is conserved. That means the strangeness before the reaction and strangeness after the reaction should be same. Okay. So let's consider, for example, pi minus plus. Otherwise, we will first consider the classes. Then, if you consider that isospin case, this is the strangeness conservation. And if you consider that isospin conservation, so in this case, your delta S should be equal to 0. In isospin conservation, your delta I should be equal to 0. And if you consider third component of isospin, third component of isospin, that is nothing but this I, and this is I3, and that will give you delta I3 equal to 0 if it is conserved. Okay. But it is not necessary that all interactions should have this conservation, because depending on these conservation values, delta S value, delta I value, we have different kinds of interactions. Unlike other energy conservation or baryon number, lepton number, in this particular case, we have a different scenario, and that will be given by this table. For example, if you consider interactions and that I3 and S. So this is isospin, this is third component of isospin, this is strangeness. First, we consider strong interaction. In strong interaction, isospin will be conserved, I3 will be conserved, and S strangeness also will be conserved. But when you consider that electromagnetic interaction, in electromagnetic interaction, isospin will not be conserved, I3 will not be conserved. Sorry, I3 also will be conserved. Electromagnetic interaction, I3 will be conserved, and the strangeness also will be conserved. And when you consider that weak interaction, this will not be conserved, I will not be conserved, I3 will not be conserved, and strong or S strangeness will not be conserved. Okay, so depends on depending on these conservations, I3 and S, we can distinguish which kind of interaction it is, and also if you have gamma particle, it is directly electromagnetic. Okay. So we have to look at these interactions. So, for example, if you consider any interaction like, let's say pi plus, which is decaying into, or interact, which is interacting with N, that is neutron, which will give you lambda 0 and plus some capitals. That count on, this is lambda particle 0, and this is neutron, this is pi. And when you consider that isospin for pi plus, first we consider strangeness. If you consider strangeness, S, so for pions, this is 0. They are not strange particles. Neutrons are not strange particles. And lambda 0, we have strangeness, which is equal to -1. You can calculate that value by using the German formula, or you can by heart it, no problem. I will provide that table for that you can get easily, or you can easily calculate by using that German formula, apply that value on number of things, and we can get this strangeness, which is equal to -1. If you want, you can do that here. So 0, Q equal to 0, and I3 you have to find out. I3 in this particular case, I3 will be multiplicity is 1, lambda 0, which is having a particle in there. So 1, that will give you, I think 1 equal to, it will be 1 equal to 2 I plus 1. So 1 minus 1, that will become 0. Right? Then is equal to 1. So that will be equal to 2I plus 1. So this will become 0. I will become 0. So this is 0, I is 0. So I3 also 0. Plus B plus S by 2. Right? So this will become 0. So B plus S equal to 0. Okay. So this is a baryon. So B is 1 plus S equal to 0. So S will be -1. Okay. So strangeness is -1. K plus, we already calculated the strangeness value for K plus. So that will be +1 for strangeness. So you can see delta S here. Here it is 0 in the initial or input. At the output stage, after interaction, before interaction it is 0, and after interaction -1 plus 1, that is also 0. Total strangeness is 0. So delta S means that strangeness before interaction minus strangeness after interaction. Okay. So strangeness after interaction minus strangeness before interaction, that will be equal to 0. So delta S is equal to 0 means that strangeness is conserved in this particular case. Now, if you consider the isospin will be for pi plus, isospin will be 1 because it is 3 particle pi plus pi 0 pi minus. If you have put it here and you calculate that I, that will be 1. And for this case, neutrons, there are 2 particles, neutrons and protons as nucleons. class of particle. So nucleons will be having neutrons and protons. There are two particles, so multiplicity will be 2, and that will be equal to 2i plus 1. That will give you 1 by 2 as your isospin. So this is 1 by 2. And for lambda 0, we already calculated that I that is equal to 0. And then we have k plus, it is 1 by 2. So consider that delta I is 1 plus 1 by 2 here, 3 by 2. Here it is only 1 by 2. So delta I is not conserved. I is not conserved. Isospin is not conserved in this particular interaction. Delta I is not equal to 0. Now you consider I3 component. I3 component for this case is plus 1. I is 1. For pi plus, it is plus 1 for I3. And for neutron and proton case, neutron will be having minus half because proton is having highest charge. So I3 will be having minus half for neutron and plus half for proton. So minus half, and lambda 0 is already I is 0, so I3 also 0. And k plus will be having plus half. I is half, k plus is plus half, k minus is minus half. Sorry, k0 is minus half. So in this particular case, delta I3 will be, check that 1 here, 1 plus minus 1 by 2. So this is 1 minus 1 by 2 is half. Here also we have half. So before and after interaction, we have I3 which is same. So delta I3 is equal to 0. So this is conserved. Third component of isospin is conserved. So what kind of interaction is this? This interaction, you can say this is S is conserved in this two. So S is conserved in this two. And I3 also conserved. And I is not conserved. So this is nothing but electromagnetic. Where you do not have a I, this is conserved. So that I is not equal to 0 in this particular case. Okay. I3 is conserved, that is I3 is equal to 0, delta S is also 0. So these two are 0. Delta S and delta I3 are 0. Delta I is not equal to 0. So that is electromagnetic. So this is electromagnetic. Now, if you check some other interactions, for example, let's say pi minus plus proton, that is going to become neutron plus pi 0. So check what is the strangeness value. Strangeness value will be S. Here, this is not a strange particle. This is not a strange particle. This is not a strange particle. So delta S equal to 0. Check what about I. For pi minus, I is 1 because it is triplet, okay, triplet particle. Pi minus pi 0, pi plus, so 3 will come multiplicity. If multiplicity is 3, then it is I will be equal to 1. And for proton, we already know it is 1 by 2. And neutron, it is also 1 by 2. And pi, we have 1. So 1 plus 1 by 2, 3 by 2 here, 1 plus 1 by 2, 3 by 2 here. Delta I will be equal to 0. 3 by 2 minus 3 by 2, that will be 0. And if you consider that I3 values, I3 value for this one, it is minus 1, so pi minus. And for proton, this is plus half. And here we have a neutron, which is minus half. And pi 0, pi 0 is having isospin, which is 0. So pions will be having isospin, which is 1. So the variation will be like 1, 0, minus 1. So pi 0 will be having that little value. That is it. And that delta I3, if we consider, here we have minus half, minus 1 plus half will become minus half. So this is also 0. So strangeness conserved, isospin conserved, third component of isospin conserved. What kind of reaction is this? This reaction is this one, right? all are conserved. So it is a strong interaction. This one is strong interaction. Now we'll look on another example. Okay, so we had the electromagnetic, we had strong interaction. Let's say another one. For example, K0, which is decaying into phi 0 plus phi minus. So check that S strangeness. Strangeness K particle, kaons are strange particles, right? So this is one. You can calculate that strangeness value. You check that whether it is 1 or minus 1. Yes, yes, here. So for strangeness, we have Q equal to I3 plus P plus S by 2. And in this particular case, charge is 0. I3 is come in the isospin. For K, there are two particles. So isospin is 1 by 2. So, and among that, K plus is having higher charge. So plus 1 by 2 is for K plus. So minus 1 by 2 is for K 0. Then plus whether kaons are baryons, they are mesons. Okay, so this will be having 0 plus S by 2. So this is S by 2 will come here. Okay. So then this we take to the other side. Then we get 1 by 2 and 2 by 2 will come. So it should give you strangeness, which is equal for case. Okay. So so that is for K0, and pi 0 is not a strange particle. Pions are not strange particles, so this will be considered. Now, if you consider for I, so delta S is not equal to 0. S is not equal to 0. Strangeness is not conserved in this particular process, in this particular reaction. So I, for I, this is 1 by 2, and this is, we know this is 1. Particles are in this group. And this is also having I, which is 1. So delta I is not conserved. And if you consider I3, this one, this is 0, so that is minus 1 by 2. And pi 0, we have I3, which is 0. And pi minus, we have minus 1. So considering that delta I3 is also equal to 0, before and after interaction, we change, if we take that change of I3, that is equal to 0. So this will give delta S is not conserved, I is not conserved, I3 is not conserved. So this is nothing but the third case. You can see from this table. Third case, this one. Not strangeness is not conserved. I3 is strangeness is not conserved. I is not conserved. So this is a weak interaction. Okay. So this particular interaction, we call this as a weak interaction. So this one. So this one is the weak interaction. So by checking the strangeness conservation, isospin or I3 components, we can say that whether the interaction is weak, strong, or electromagnetic. Also, I already told if gamma is present, directly it is electromagnetic because these are photons. Okay. Also, you have to understand that leptons, if you consider leptons, these leptons do not have that isospin. For leptons, there is no isospin. Why? Because isospins are introduced in order to understand or distinguish the particles under strong interaction. For example, if you consider nuclear interaction based on the nuclear force, for nuclear force means that strong interaction, strong force. So in nuclear force, if you consider proton and neutron, you cannot distinguish whether the particle is proton or neutron, because nuclear force or strong interaction is independent of the charge. Okay, nuclear force or the strong interaction, which is independent of charge. So it does not consider whether it is positive charge or negative charge or neutral. The interaction will be same. Strong interaction does not depend on the charge. So in that case, these protons and neutrons, if they interact through strong interaction, through nuclear force, then such interactions, in such interaction, we cannot distinguish whether this is proton, whether it is neutron. Okay. So in strong interaction, if you want to distinguish between proton and neutron or any other particles in strong interaction, we cannot distinguish them by charges, because strong interaction is independent of charge. So then we have to have some other quantum number to distinguish these two particles, so that we introduce this isospin. So in that case, this group will be having isospin 1 by 2, and for proton we have plus 1 by 2 I3 component, and this is minus 1 by 2. Now we can distinguish these two particles, because this is plus 1 by 2 and this is minus 1. But in the case of leptons, so this is the reason why we introduced those isospin concept, because we cannot distinguish the charged particles or uncharged particles in this strong interaction. But when you consider leptons, okay, electron, lepton, muon, or towons, that group, electron, muon, towons. So these electron, muon, towons, or any leptons we consider, or their antiparticles or their neutrinos, or those things, if you consider any of these, then these leptons will not be interacting through strong interaction. So this will not interact through strong interaction. Strong interaction. That is not possible. They will not interact with each one other with strong interaction. That is not possible. Okay, so leptons do not interact each other through strong interaction. Because of that, we do not consider isospin for these leptons. We do not have to consider, because we already know that electrons are having positive charge, neutrons are having negative charge. When they interact through this weak interaction, okay, through electromagnetic interaction, uh, at that time we can say this electron is having positive charge, positron is having positive, sorry, electron is having negative charge and positron is having positive charge. That we can say, because there is no strong interaction is happening, because they interact only through weak of this electromagnetic. In those cases, we can distinguish them by through their charges. Okay, so for leptons, we do not apply this isospin. That there is another point. Also, when you consider the isospin, we already said that isospin will not be conserved in electromagnetic interaction. That you just study this step, okay, for all those concepts, which means that isospin will not be conserved in electromagnetic and weak interaction. It will not be conserved in weak interaction. In the lowest, strangeness will not be conserved in weak interaction. So all those things we have. Okay, so that's all about this strangeness and isospin conservation, and determining the reaction type, which kind of. So basically, we have to consider whether the reaction is possible or not by using those energy conservation, momentum conservation, then parity, sorry, baryon conservation, the lepton number conservation, those things. If that is conserved, then only that reaction is feasible. Those reactions are possible. And if you consider strangeness and other isospin, strangeness is conserved in some reaction, but it is not conserved in weak reaction. Strong and electromagnetic strangeness is conserved. Similarly, isospin is conserved only in strong interaction, in electromagnetic interaction. So by using these conservation laws of strangeness and isospin, we can say whether the reaction is which type of reaction is So that's all about this strangeness and isospin conservation. In the next class, we will deal with